Welcome to Alchemy Wizard. I'm Tom. This is part 2 of our laboratory experience. I want to pick up where I left off on part 1. In part 1, I cooked iron, colloidal iron, 99.99% pure colloidal iron disc, using sodium citrate. And the waveform that we got was quite strange. It looked a lot like colloidal gold waveform. And it kind of baffled me. And that's where I kind of ended my discussion on that in the last video, that I was going to explore it. And I did lots of exploring. I went on a whole crusade of exploring colloidal gold and what's going on with colloidal gold in the background. And that prompted the last video that I published on colloidal gold, my findings there, which wound up being a sidebar to everything, because this is what happened. I cooked colloidal iron, and I learned a lot in various different ways. I used citric acid. I used various combinations of malic acid and other things to try and see what I could do to get a stable colloidal iron here. And I learned a little bit about the process here. But the big thing that I learned after, I tried a lot of different things, I said, let me re-verify my sodium citrate stuff. So I cooked up another batch of sodium citrate, and using sodium citrate, I dripped the current to 5 milliamps, let it cook, and then I got this fluid here. And this fluid actually is this picture over here, and it's actually pretty good. What happened was the beaker that I used when we made the video, I had just cooked colloidal gold in it, and I didn't wash the beaker properly. And because of that, that's why the waveform was a lot like colloidal gold when I cooked the colloidal iron. It looked like colloidal gold. Well, it looked like colloidal gold because, hey, guess what? It had colloidal gold mixed in there. But that's okay. That birthed the whole investigation on colloidal gold, and you can, watch the last video I published. I'll put the link in the description of that, of my results of what I found on colloidal gold. But anyway, it winds up that you can effectively cook colloidal iron with sodium citrate, and it's actually the better way to go. And the reason is something called iron oxide. Iron is, when you take iron and you drop it in water, it starts oxidizing right away. I mean, fast. So, just dropping it in water, we're creating iron oxide. And that brought me to understand that the longer you take to cook colloidal iron, the stronger the iron oxide is going to be. So what we want to do is cook this as quick as possible, because we want the iron oxide to be as low as possible. So that brings up to a couple things that you need to be aware of. A, you don't use an iron anode and an iron cathode, because now you're going to be increasing the iron oxide in the water. Don't cook your colloidal iron for longer than an hour. Keep your current around 5 milliamps. You will either use my stock solution and drip in the sodium citrate until it hits about 5 milliamps, or you can sprinkle the sodium citrate in with like a granule or 2 at a time until you hit 5 milliamps there. And don't cook it for more than an hour. I would not even cook it to this depth of color, because even this depth of color is going to have a strong iron oxide flavor. That would be my recommendations. I personally prefer the stainless steel. Stainless steel is an amalgam of several different things. It's got mostly iron in it, but it also has chromium, and it has some nickel in it. It might have something else in there. I'll have to look up the contents of stainless steel. But as you know, I have a start to finish on cooking stainless steel, and that does, because it's an amalgam, it doesn't oxidize. The iron does not oxidize as quickly, and the taste isn't as strong. If you don't want any iron oxide in your iron at all, then I recommend plasma arc if you have that set up. And with that, it cooks really fast, and you don't get any there's very little iron oxide in the water, basically using stainless steel with plasma arc. I have not tried plasma arc with iron, but again, we're going to wind up with the same problem. As soon as we put the iron in the water for the plasma arc, we're going to be creating iron oxide. So that would be my recommendation. But for those of you that want just an iron-only solution, sodium citrate will do it. Okay, now that we got iron out of the way, let's talk about my laser process. Because that is, I think, really exciting, and there's a lot of interest on the internet about it. So here we have the new rig. It uses ball joints instead of the screws to hold it in place. My gosh, it is so much easier to just move these things on a ball joint and get them all focused into the center here. So let me just show you that for a second. What I got going on here. All focused. As you can see, I got the glasses on, so I can't see it, but you can see that we got the laser coming in here into the bottom. And what I'm cooking in here is zinc. Out of all of the metals that I've done so far, magnesium, gold, copper, zinc was the only one that I couldn't create a stable colloidal out of. Let's turn this back around. For some reason, the zinc colloidals, they weren't very high, and there wasn't a whole lot of them. And that's the only metal that I had trouble with. Generally speaking, what I've come to find is it takes about 300 minutes to cook a colloidal with the laser light penetrating it to get it about 12 parts per million. But I don't know, that could change as I get more efficient with the process. This top definitely makes it much more efficient. I can also cook it for longer periods of time than I thought. Originally, I only kept the laser going for 10 minutes because I didn't want to burn the lasers out. Well, I did an oops at one point, and I forgot that I had the laser process going, and a couple times I went for over an hour with the lasers going, and I had no problem. So I'm thinking I can successfully maybe do 30 or 40 minutes at a time with these lasers and not have a problem with them. So that may shorten the process down. But from my test, 300 minutes gave me about 12 to 15 parts per million colloidal out of whatever metal I used, except zinc, which was really low. So I'm recooking zinc because, like I learned with the iron thing, and with any experimentation, if you do it once, it doesn't mean you can do it again. You have to be able to replicate the process over and over again before you can turn around and say, success, I had success. And it's the same thing with this laser project going on here. I'm doing various metals, testing them out, putting them in the microscope. I'm going to redo them and just see if I can revalidate this process again. Because it's weird. I mean, I've talked about it. Originally, my thought with the laser thing was we were going to use laser ablation, which melts the material off and creates a colloidal. That's generally, they use a high-power pulse laser to do that. And the temperatures of the laser are extremely high, much higher than the melting point of the metals. I figured we could, with the 4 lasers combined together, they're 5 milliwatt lasers. I figured we could probably do maybe magnesium, maybe zinc, because they have low melting points, about 800 degrees C. When I moved on to other metals, especially like vanadium, which is a really hard metal, and I got a really high colloidal content from it, I realized something else is going on. We're not melting anything here. These lasers aren't hot enough for that. What I think is happening, that me and my chemists have explored it, is something we're calling photon-electron excitation. And what we believe is happening is the photon energy from the laser light is energizing the outer electron in the atom and causing it to gain so much energy that it can no longer stay part of the metal. So it flies off out of the metal and into the solution. So we get a bunch of free electrons now floating around in the solution. But the other process is what happens is once that electron separates, the atom also separates from the metal and is now floating in the solution, which is now full of all of these free electrons, and they then get sucked back onto the metal to create a neutral charge particle, a nanoparticle. So we believe that's what's happening with all the metals that I've tested so far. So zinc is being a retest right now. See why maybe something wasn't right with the water or something, and that's why I got a very low zinc count. But I'm sure as this process, as I get more familiar with this process, and then we get all the little kinks and bugs worked out of like the lasers, I'm sure it's going to get much more efficient than it is now. So eventually I will have the blueprint for this top in the on the website, though not yet because I'm still working on it. And once I'm done working on it and I feel it's stable enough, then I'll release the blueprint for the laser top. So that is the laboratory experience part 2. Let's see how that's doing. All right. With that, I'm going to say, if you made it to the end of this video, you've earned yourself another cool. I'm Tom, Alchemy Wizard. I will talk to you again soon.